So thanks a lot, everyone, for joining. For those of you who don't know who I am, my name is David Rodríguez. I'm a research scientist at eSpace, the EPFL Space Center. And today I'm introducing you to something pretty new. I guess this will count as the official introduction to something we've been working on for a while now. And we call it the Lunar Hub. So this presentation is going to be a bit all over the place, as you'll see. So I'm going to start by giving you a bit of a more of a brief introduction really to who I am and why I'm speaking about this and why you should listen to me. Then I'll move briefly to explain for those of you that may not be that familiar to what we do here at eSpace. I just have like 10 minutes of introducing to you what we do, the different initiatives we have, and how the Lunar Hub kind of like makes its room through everything we do here at the center. And then I'll dive right into what the Lunar Hub is, what we intend to do with it, what's our objective, and the projects that we have running as part of it currently. So let's see if I can control this. So among this apparent chaos, there is some cohesive net to it, and that is, let's say what we're going to try to do with the Lunar Hub and the projects that we're kickstarting all have a connected tissue, and that's how we can actually make a significant impact on the efficiency of exploration. And there is two words in there that I highlight that scientists tend to go like turn their heads and say, I don't quite like those. One is significant and the other one is efficiency. So I'm going to try to define those quickly. When I talk about significant impact, I'm talking about first let's touch upon efficiency. So upon efficiency, I'm talking about two main things. One is how we can actually explore for longer durations and also longer distances, right? That is somehow a flawed analysis or a flawed definition, but it is the one I'm using. Right, so if you can come up with other ways of measuring efficiency, and it's not perfect. You could say, well, you can actually be very efficient in a very short distance if that you are exploring is actually very valuable from a scientific point of view. Right, from my side, just to have a definition that we cannot agree upon, I'm using that. So meters per year of exploration, meters per 100K invested on every mission. That's my efficiency rate. And then when I'm talking about a significant impact, I'm mainly using two metrics. One is that I want to increase in 2 orders of magnitude the meters per year of exploration that we are able to do. And then I want to at least double the amount of meters that we explore for every 100K invested on every mission. Okay, so this is kind of like the general framework among that chaos that you will see based on the different projects that we have. So, okay, very quickly over this, who am I? So my background is in mechanical engineering. I actually started my career working on solid mechanics. I started doing research on ballistic impacts on composite panels. So trying to model how those panels that at the time were primarily used in aerospace, were breaking, upon an impact of high speed impact. So we're trying to model that, trying to understand how they fracture and have a better understanding of how they behave under those strain conditions. I did some work also for ESA on that realm, more related to the topology optimization of antenna brackets for Earth observation satellites. But then I wanted to work on something that was a bit more hands-on. So I started to move more into robotics. Started to work with the automation and robotics section at the European Space Agency. Moved to Japan, did my PhD there on high-speed robotic locomotion for lunar missions. And that brought me here to EPFL when I'm doing research on lunar-related subjects, as you will see, mostly related to robotics. So that's pretty much what I've been doing in a nutshell. So we are here. The Space Center is just it cannot be any closer to Lac Le Mans, I guess. And the reason I like to show this picture is for those of you that aren't familiar, this tends to bring people or to increase the interest of people to come to work with us more than any of the other slides I have in my presentation. And I kind of know why. So here we are. You can see Mont Blanc in the background. It's actually the only the peak that remains white all year round, so easy to identify. So yeah, there's where we are, and here's the team. Small drawing of the team. So we have our directors, so Jean-Paul and Emmanuel, who are our bosses, directing both from an academic point of view and also in terms of just projects and general strategy, the center, sorry. Then we have people working on communications, administration, operations in general, the people actually running and making sure that the lights are still on. So Candice, Thomas, Stephanie, and John. We've also people working on debris removal, active debris removal, and innocuous servicing. So Simon and Nicola working also very closely with ClearSpace. People working on space sustainability rating, which we started operating this year, Adrienne and Florian. Mathieu, who's here with me in the room, working on space sustainability, space transport and logistics, and myself working on lunar. So we have quite a wide range of backgrounds and expertise in the center. And that goes along what we also try to do. So we have three main pillars at eSpace: education, research, and innovation. On the education front, we try to inspire the next generation of space talent. We also coordinate the minor in space technologies. And on the research side, you may be able to infer from the spectrum of backgrounds that we have two main kind of like lines of research, if you wish. One is on sustainable space logistics. The other one is on lunar related aspects, which is the one I'm going to talk more in depth about. And often we also work alongside industry, both national and international companies. So we kind of have that going on in terms of innovation and technology transfer. Okay, so what's the Lunar Hub? What's this new thing? So when I joined the team in 2 years ago in 2020, we started discussing about the possibilities of getting involved in lunar activities, and the reason for that is that it was very obvious for us that there were some knowledge and technology gaps in all this exploration and infrastructure development roadmaps that we could actually attempt to bridge by just connecting different actors, right? So one would be us and our own expertise. The second one would be EPFL labs that were working on technologies that weren't necessarily being applied to space, but they could, and they had like high potential to be applied to space. And then opportunities out there, right? So opportunities to bridge these gaps that were coming out due to the this renewed interest in lunar activities. And with that, we started what at the time was known just simply as a Lunar Research and Technology Development Initiative, now renamed Lunar Hub, and we're trying to do a lot more with it. So what is it that we're going to do? I mean, in that broad kind of like scope, you can do a lot of different things. And what I decided that we were going to do is to focus on the earliest stages of the lunar exploration and infrastructure development roadmap. And in particular, sorry, I'm going to just move this here so you guys can also see it. In particular, so in those earliest stages of lunar exploration and infrastructure development roadmap, there is three key steps, right? Like you go from orbital observation to ground exploration to then the production or whatever comes after, where things are. So for us, we're going to focus primarily on the second one, which is exploration. And that involves three main things. So it's all that is happening on the ground. That's ground truthing, ground prospecting, and resource mapping activities. And just to give you more of a grand sense of what we're trying to do, this will go all the way from ground robotics, which is primarily where we're going to focus on, at least for now. Access to extreme locations, permanently shadowed regions, skylight, extreme topographic regions, in-orbit teleoperation, the characterization of those regions. So identifying, mapping, interesting, resources or just scientifically valuable regions, mission concept design, and also the design of instrumentation, right? So payloads that these robots will carry to these regions. So that's the Lunar Hub. And now what I'm going to do is I'm going to give you just some high-level hints into the 4 foundational projects that we currently have ongoing as part of the Lunar Hub, which are the ones you can see here, kind of like the verticals. Those will be the 4 foundational projects we currently have. What you see at the bottom are kind of like the main areas that these projects touch upon, right? So it's robotics, it's multi-robot cooperation, there's scientific instrumentation development, is fast mobility, fast autonomous mobility, and mission concept design. So let me start with the first of those foundational projects, and that's the Lunar Reconnaissance Drone Project. This is a project that started with the idea of looking at how commercial drones were being used here on Earth, and also kind of like the hype that went alongside Ingenuity for Mars, and the possibilities of having something with that level of dexterity in low gravity celestial bodies, right? What would be the solution that could bring that level of dexterity to other planetary systems? And with that idea in mind, we started to look at, okay, what are the technological solutions that we can actually use for, or in order to have something that is autonomous, airborne, quote unquote, lightweight, compact, and reusable, in particular for, in this case, for lunar applications. And with that idea in mind, we started assessing, okay, what is it that this technology will need to look like? And the prime, or 2 of the main use cases for the use of this hypothetical lunar drone would be the exploration of permanently shadowed regions and the exploration of lunar skylights. The reason for those 2, in case you aren't familiar with that, one is because the prospecting or imaging these regions from orbit is actually pretty hard. So we don't have high resolution maps of permanently shadowed regions. And the reason for that is because there is no light there. So we need high exposure times, which also means a higher level of noise. I think the resolution, the highest resolution we have from images taken from orbit is around the 10 meters per pixel, which is far from being enough for follow-up, on the ground prospecting missions. And then in terms of the lunar skylights, what's obvious, that's underground. So we actually need to go there and see what's resting or what's awaiting for us under those potential entries to these tunnels, right? Underground tunnels and caves. So we need to be on the ground. We need to be close to the ground, and we need to map and characterize these regions with a system that allows us to do that. And doing it with something that can actually fly over these regions is a lot more effective than actually something that needs to drive over them, mainly, again, because we don't know what's awaiting for us. So in terms of general concepts, just so you have also a bit of more of an idea of what we're thinking about. And this is an old concept. We've changed things as we speak, since we have people working on it at the moment. So the general idea that we also wanted to have is there's something that is actually, again, easy to use, right? So the first thing we struck out of not being easy to use is landing on the ground. So we wanted to have something that can be used on top or alongside any other robot or vehicle on the moon. And initially we started with this concept of a service station that lands on top, that is actually seating on top of a vehicle. That service station will have all the refueling tanks for the drone. It will handle all the communications, the recharging of the batteries, and it will serve to take off a landing pad for the drone as well, right? And when you get to that point, let's say the edge of one of those permanently shadowed regions that you would like to explore, but you don't have a precise or high resolution map down to the centimeter level that you will need for proper planning with a rover, for instance. Then at that point, you will deploy this drone. So deploy this drone, map the area, come back, share the map with the rover, and have a proper path planning a lot more efficiently than otherwise, just getting in, taking panoramic images, coming out, sending those images back to Earth, having humans look at those images and see what's our next destination, right? Which is how we do things in real life. So this has changed a bit. Now we don't have the service station on top of a rover, but we're actually carrying a trailer with us. The reason for that is that way we don't affect the design of the rover as much. So it will be just that mechanism for the docking of the trailer, so that the rover can actually just tow the trailer with it. That's the only main difference. Again, a little bit more details without getting too much into the into the specifics. Right now, what you can see here is just the skeleton of course, there's a casing that goes around it, but this is so that you can actually see what the drone looks like at the moment. Very low mass of 17 kilograms so far, drawing about 325 watts. This has an overall envelope of like 50 by 50. It can fly at about 50 meters above ground level for about 800 meters. So that's 120 seconds if we got max speed. And the idea is, again, there's only one main instrument, and that's the one that will be used for the imaging, kind of like high resolution mapping of whatever it is that we're exploring. Initially, we started with a flash LiDAR as a potential solution. Most likely it will be swapped by an instrument we're developing in-house here at EPFL, which is called Dragonfly, and I will talk about it. I think it's one of the last projects I'll mention. Well, and I did mention this, but of course this is moving, with 4 monopropellant thrusters. At first, we're just looking at hydrogen monopropellants. Ideally, we should move to hydrogen peroxide-based monopropellant thrusters to then make the case of reusability even stronger if we add the aspect of in-situ resource utilization. You'll be able to produce that hydrogen peroxide from the resources extracted at the place of exploration. But for now, very preliminary, and this is what we have. This is more or less the same, so I think I'm going to skip this one. This is just kind of like a configuration diagram of what you saw in the previous slide. So I don't think it's worth looking into this. We're also working at the moment on the control aspect of such a drone. There's 2 master students, Daniel and Hippolyte, working on this at the moment. And there are some of the animations that they've been putting out on, just because this is one of the key components, the propulsion system and the controllability of rocket engine is quite different from that of, like, say, propellers, right? So it's an aspect that we have to look deeper into, and then it's probably the next steps would be getting away a bit from the high-level design, high-level system design, and more into the specifics of such a propulsion system. So how we can have that rapid, precise control with in this case, hydrogen peroxide monopropellant engines. So that's one of the things that are coming, as I said, the precise control. The other one is this change in the concept of operations, of not having a service station that is allocated on top of a vehicle, but rather have a trailer that can be connected and just carry it to wherever is interesting. This adds also a kind of like a layer flexibility, because while the drone is being used, the rover can be actually used to explore nearby regions, which previously the rover would have to wait somewhere for the drone to come back. In this case, we add that level of flexibility, and the idea is, again, to keep this very low mass, below 100 kilograms overall, with everything included. So the tanks, everything is being sized for about 10 flights without recharging the tanks. These are the people that have been working or are currently working on the projects. I just want to show my appreciation for all the work they've been doing. And I'm very lucky to count with all of them, and really grateful that they of the work they've been doing on their projects. And thanks a lot, guys, for the help. So the second project I'm going to talk about is actually the continuation of what I was doing previously before joining EPFL. So most of the things that I'm going to mention now actually belong to my previous research and that research that was done at the Hockey University, the Space Robotics Lab there, also together with the European Space Agency and the German Aerospace Center. So everything I mentioned, again, it was something that was done before, but it's on the subject of fast off-road mobility, right? As I said, how we can actually increase in 2 orders of magnitude the speed of exploration. And so the number of meters that we do per year of exploration. And here, I'll briefly give you some details on the results that we had on the aspect of locomotion. But my idea is also to touch upon aspects related to navigation as well. And when I say fast in this case, it's over 100 meters per second. So again, you see the 2 orders of magnitude increase in speeds there. Current rovers don't necessarily move beyond 5 centimeters per second, 5 to 10 at most centimeters per second. 10 is already pushing it. And we can discuss later on the reasons why that's the speed and why we move so slow. So the focus of the research again is one was understanding what is going to happen when we start to move at those speeds, right? So try to understand what was the physical phenomena governing, which is not necessarily fast if you see it real life, like it's just the speed of a human walking. But when you start to add the layers of complexity that we often have in space, like, well, we don't know necessarily how the ground looks like. We don't have a lot of details on the mechanical properties of soils, reduced gravity, and so on, then autonomy, then this becomes increasingly complex. Then is once we know, okay, these are the physical phenomena actually governing these processes, what are the dynamic effects, how we can model those dynamic effects so we have better predictions on what the performance would be, and then how that could impact the design of systems, right? As initially, I'm going to talk about more on the locomotion side of things, which actually is affected by 2 main aspects. One is traction, and the other one is suspension performance. On the traction side, if you've been following the news for the past decade on Mars exploration, you may know that most, if not all, rovers have suffered from, wheel-soil interactive effects, right? Almost all of them, I believe, they were stuck at some point on some like sand dune in the middle of nowhere. That would have probably, that could have been the, or mark the end of the mission for some. For others, it was a big thing to deal with and a big problem. And again, it's coming from that lack of understanding and complexity in predicting the performance and understanding that interaction that we often have. And that's what that branch of research and science is called terrain mechanics. And that's what we try to understand at speeds that weren't necessarily the ones we're moving, but actually a lot faster. What happens when we go a lot faster? And then suspension performance, how we can actually improve our mechanical systems to attenuate the new loads, the new vibrations coming out of moving 100 times, let's call it 100 times faster than we used to. So I have a little video here showcasing a bit of what we did, so you have just a general idea, and also I can stop talking for a bit. May have some music. I don't know if the music's playing or not. Is there music playing? It's very faint music. Otherwise, I can explain what's going on. There's no music? Okay. Never mind. I'll talk to you about it. It was just some epic music that I was kind of proud of. So these are part of some of the results that we did thanks to the people at the German Aerospace Center. So this was actually the only place I could do the test that you're going to see now. Because if you can imagine, like if you want to do some like wheel-soil interaction test at 1 meter per second, you need a big enough sandbox. And usually they aren't that big because for space, we use like this. These are called single wheel test beds. And these tend to be quite small, like 1 meter to 1.5 meters, because we move so slow, like 5 centimeters per second. With 1 meter, you have more than enough to have representative data. But to move at 1 meter per second, one, we needed a big enough sandbox. And the second one, we needed something that moved as fast as the wheel. So this was the perfect use case for the troll lab at DLR, and because they had this, like you saw, the cook arm moving or used as a guidance for guided mechanism for the wheel. So these are some of the kind of like the videos that we recorded just to see, okay, what was happening with the wheel. I believe this was an acceleration that we performed from 0 to 1 meter per second with one of the most complex soils we used. So we played with as many different soils, as many different wheels, as many different conditions as we could. Again, the idea is just try to understand what were the physical phenomena actually governing the interaction between high-moving rovers, fast-moving rovers, and different soil simulants. And I believe the video ends here. This is just a cool other video that we recorded. So one of the issues of working with soils is the repeatability of tests. So soils in general are highly affected by humidity, temperature, and so on. So you kind of need you need a control room. You need kind of like is kind of like the opposite of a clean room. So you need something that is controlling temperature and humidity, but you can keep all the dust inside. And in order to prep the sandboxes for each experiment, we use what you just saw, which is a fluidization. So compressed air that was being blown from the bottom of the sandbox just to completely flatten the surface layer. This was one of the mechanisms. I'm not going to spend a lot of time on what we found, but just so that you don't, I don't finish this presentation with, we work on this and then you go figure out what we discovered is that, and this again is in general terms, that the performance wasn't that much affected up to speeds of about 20 centimeters per second, right? So for those up to that level, looking at different metrics, so Drover pool coefficient, which is just the level of net tractive force that we had at any given time, the level of wheel sinkage, and in general tractive efficiency didn't decrease as much in general across all the cases that we studied for up to 20 meters per second. And then what was interesting is that beyond that number of 20 centimeters per second, we started to experience with almost every simulant we used a different behavior in that interaction. So a lot more fluidity in the soil moving from kind of like a solid state into a more like a liquid-like state that would make even harder to model. So that's some of the things we found. Also, just in general terms, you're working on ferromechanics, you also know maybe that there is a rule of thumb, like maximum efficiency is often reached at 10% sleep ratio. So we saw that level of sleepage at which you reach maximum efficiency, tractive efficiency, was actually shifting, increasing with the speed. And also another thing that is often kind of like a running heuristic in the field of ferromechanics, which is that robot pool increases with the sleep ratio. That also didn't happen for speeds beyond 40 meters per second. In terms of the different wheels that we tested, also in this case, flexible wheels were still the best performant wheels, also at lower speeds. So if you ever have to choose between rigid or flexible wheels, just go with flexible wheels. And it's upper and wide. I mean, it's just a harder surface area than to also work better in this particular case. So what's next? As I said, this is a lot. What I just explained had to do a lot with locomotion and so traction, suspension design. I didn't mention much suspension design. I don't have a lot of time, but I'm happy to answer any questions if you have some. The aspect that I would like now to start to look into as part of this newly created Lunar Hub is the aspect of navigation, right? Like, okay, now that we have the mechanisms to actually move faster, we understand how that works, how that impacts, motion control, how that impacts all the GNC architecture, localization, mapping, and path planning processes so that we can actually make our navigation a lot more effective, increase duty cycles, and so on, and how we can have that actually running on chip instead of having to wait downlink all the data and do all the heavy computation here on Earth. That's some of the things we want to do. We're also looking at different mechanisms, so actuated suspensions together with Explore, which is a student association working on space robotics here at EPFL, looking at more on the aspect of actuated suspensions so that we can precisely control the configuration of the rover at any given time. And that's it on the fast mobility side. Another aspect that I would like to start looking into as part of this Lunar Hub, and here I don't have a lot of information, so I'm just going to give you the brief idea of what we're trying to do, is to start to look at the aspect of heterogeneous multi-robot cooperation for exploration and science in extreme environments. And when I say extreme environments, in this case, we'll not just stay in like planetary environments. We actually would like to understand and analyze and study the potential deployment of these teams of robots, which just to be clear, I'm talking about swarms. So this is small, I say they're low cardinality, so a small number of team members, lower than 15 per team, can be deployed in extreme locations also here on Earth, right? And we're gonna look at, how to effectively cooperate when we're exploring extreme locations, how to perform all the task allocations for the different robots, what the robots need to do, and when all that. We're gonna start to look as part of this foundational project. Well, and as I just said, I'm just using this image from EPFL's Extreme Environment Research Lab, but the idea is also to deploy these teams of robots, not just on the Moon, Mars, and other planetary systems, but actually to look at Earth, talk to the scientists, doing field campaigns in really extreme locations that they may need of the capabilities of these teams, and it could be really a useful platform and for them to perform the work they need, so that we can stop relying or rely less on humans on the ground for some of these dangerous activities that we still need to do. And then the last project I'll mention, the last foundational project I mentioned is our project Dragonfly. I briefly mentioned it on the aspect of the drone, that these will become potentially part of the payload. So the idea here is that we are developing a very unique camera for space. And the reason why it's unique is because we are actually fetching from a technology developed at EPFL's Advanced Quantum Architecture Lab, and that's a 1 megapixel SPAD sensor. So SPAD sensors are a different technology that use single photons. Well, actually SPAD means single photon avalanche diode sensor. And the difference between a SPAD and other sensors you use, like CMOs or CCDs, is that with these sensors, you actually have a much higher sensitivity to the point that you can actually count light. So you will be able to count individual photons impacting on this sensor. And this camera has been used so far for many different applications. You just show here a short video on the first time that super luminosity was actually witnessed in the lab, I believe. Please don't explain me to or don't ask me to explain what superluminosity is, but it's just kind of this apparent is the apparent speed is the speed of light that looks like it's moving faster than actual speed of light. So you will see there some of this experiments that were done, and this has been proven, and it's in a paper. I'm happy to give you the reference. But as you can see, just explaining this, I'm probably struggling, so don't ask me too many questions here. And so this is, again, coming back to understanding those, or identifying those gaps in the roadmaps and trying to see what expertise we have actually here at EPFL and what can be done. This is a clear example of that. So this camera that was used for many different applications, we started to look at the possibility of actually implementing it in space. It has two main applications that we're looking into. One is prospection, and the other one is navigation. And the reason for that is because these cameras, they tend to be very fast. So we're talking about frame rates that go up to 25,000 frames per second, if not higher. And as I said, they are very sensitive. So the dynamic range tends to be way better than traditional optical sensors, or the traditional technology using optical sensor and cameras. So what you can see here, for instance, this is an image taken, bright daylight, window behind the target, a lamp pointing at the lens, and everything is clear in the image, right? So this is something that is very hard to achieve otherwise. But this is just a very clear example. So one of the things that we're looking into is extremely low light photography, for instance. Again, coming back to the exploration of those regions on which we probably don't have any sunlight, PSRs and skylights. And yeah, I mentioned, without giving details, on like this has been used for multiple applications. One is this kind of like validation of the superluminal motion in the lab. So the 4D like light reconstruction in flight that you just saw, apart from many other applications more on the biological sense that I don't really understand. But it has tremendous applications, and now we're looking at the potential application of this on a space. And what we're trying to do is moving from taking the camera as it is right now, which is in a very like proof of concept in lab status, and moving it into something that can actually be deployed in space. And that's reducing the overall footprint so they can actually fit in less than 1 unit of a CubeSat, designing the interfaces so that we can work with other subsystems and so on. So that's what we're working on right now. And on the side, another interesting thing that we want to do, let's say alongside the development of this, of the hardware development that goes in making this system space ready, is all the edge computing that will be needed so that we don't rely as much on high or like heavy computation here on the ground. So we want to do on-chip post-processing of the images. And for this, we're also working on how to actually accomplish this so that the payload can perform and be used in as much of an autonomous fashion as possible. And again, as I mentioned before, this goes in for applications, it goes into navigation and prospection as well. Part of our goal is to have this ready in 2023 so that we can start performing in orbit demonstrations as soon as late 2023, early 2024. That's one of the reasons we're just reducing the footprint, so that as soon as we have an opportunity to fly this to space, validate the data pipeline, prove that we can actually take images that are better than with other technologies, and also do the post-processing on board without requiring like ground intervention. We're gonna take that opportunity. And on this side, we're also a partner of the Moon Village Association payload project, which is attempting to launch or to place a camera on the surface of the moon to take images of Earth and try to reenact the overview effect. So here we've been partnering with them. We've been partners of the project for almost a couple of years already, and we're moving into the end of the phase B of this mission, and which is quite exciting as well. And we'll be using the exact same technology. So I think that with that, I will wrap it up. I'm really sorry for the kind of like the stream of information, but I wanted to just try to cover as many details as possible from all the different projects that we're trying to do as part of the new Lunar Hub, and I'll be happy to answer any questions you may have. Thanks a lot.
Thanks, David.
No problem.
So we do have a question. Marcus has a question. So Marcus, you should be able to ask now.
Yes, thank you very much, David. It was a very interesting presentation. Very much appreciated. I have a question about the drone that you've shown at the beginning, and you've mentioned here that you intend to use hydrogen peroxide as propellant. So I don't know in which detail you have investigated this aspect. For sure, it's a green propellant, and you can use the in situ resources on the moon for this refilling option. But when we have investigated a monopropellant version of hydrogen peroxide, it was not so responsive, the reaction. And you have already checked this a little bit, this aspect?
No. So the quick answer is no. This is something that we haven't looked into. We just have like the hints of the directions that we would like to explore. And actually, this is something that I'm actively looking for. People I can partner with a lot more expertise on this area than I do. As you could see, probably in what I've been doing, there's nothing about rocket engines or propulsion. So this is something like quite new to me. And so for now, we've just been looking at the preliminary design, just in general sense. What is it that we would like to do? And now, from now on, is the point we're going to start to look into all these aspects, right? Like, okay, from a point of view of controllability, is it actually possible with something like hydrogen peroxide, or do we need to look at something else? I'm sorry, I don't have an answer there. I don't know yet.
No, it's very fine, Tom, and thank you for this answer. And as said, I think it's a very interesting solution, hydrogen peroxide. And well, you can contact myself on this aspect when you would like to have some more details, because in my actual work at the exploration company, indeed, we are working on hydrogen peroxide propulsion systems, and we have tried to find out which expertise is given in Europe on this propulsion system. But feel free to contact myself. But thank you very much for the presentation once again. It's very interesting.
I'll definitely reach out to you, Marcus. I'll send you an email.
Okay, great.
Okay, so we have another question. Where is it? From Max H. Is gravity an important factor for soil behavior regarding rover tires?
Well, so yes, the quick answer is yes. So gravity is an important factor for traction in general, but it impacts soil behavior. So it impacts the level of compaction that we can expect. There are other factors. There's thermal cycles, so that also can affect that. But gravity definitely is a factor that we should take into account. And actually, one of the coolest projects that I saw on this, would be the MMX mission. So the MMX mission, which is I believe is CNES, JAXA, and DLR, planning also to deploy a wheeled rover on Phobos. That will be pretty challenging, right? Like being able to achieve enough traction to move a rover on a very tiny celestial body, it will be interesting. So we will be able to get a lot more information there. So alongside, I mean, it's definitely an important factor. So you need gravity is what helps us move forward. And the lower the gravity, the more challenging it is to actually stay on the ground. Hope that answers the question.
I guess it does. And there was another one. What is the time frame for the two previous projects you presented?
Okay, so the two previous projects, well, okay, I'm going to give a time frame for all of them. There were 4. So for starting from the last one, so Dragonfly. So that we actually partnered, and I'm very grateful for them too, with ArmaSuisse for that one, for the initial phase. So my idea for that project is that we would have a breadboard / engineering model by the end of 2023, but very close to a flight model configuration, so we can, as I said, have an in-orbit demonstration as soon as possible. So if there is a slot late 2023, we'll make it happen. That's for Dragonfly. For I guess the other one where the timeline is important is the lunar drone. There's no timeline there. Now we're moving more into the research side of things with the propulsion capabilities, the control aspect of that. So no real timeline there. And then the others are also open. So, Hermes, I didn't mention Hermes, but the heterogeneous cooperation with multi-robot teams, that will be an ongoing theme. There's so many aspects that we need to look into that, like multi-robot task allocation, effective exploration with multiple robots, etc. So multiple things to do there. And same for the fast mobility, right? Like that's just an ongoing project.
Okay, thank you. And the same person has a question again. I'll unmute her.
Hi, thanks a lot for your presentation. My name is Charlotte Nassi. I work for iSpace in Luxembourg. And I was just wondering if there's any specific lunar data that you are currently missing and that could potentially help you in these projects.
Sorry, you said any specific what?
Data, environmental data about the moon.
Yes. So, sorry, I'm gonna mute here because otherwise I hear myself twice. There's so many. Okay, so on the aspect of mobility, if we're just talking about terrain mechanics, is of course understanding what the soil looks like in South Polar regions, right? So far, we just have expectations. So we know that, they're affected by, probably less stable, more extreme, depending on when you define it, thermal cycle. So compaction may be potentially higher there, but we don't know. So understanding the, how the ground actually looks like, that's something, as far as I know, that we don't know. We just have expectations. That's on the aspect of terrain mechanics. Then, I mean, I don't know if from an environmental point of view, we actually need that information, because for I was thinking like, okay, what other things are very hard to actually model here on Earth, and there's a lot to do with the aspect of lighting, but that we can actually get it pretty close to what it may look like. And so recently I was, for instance, at the Lunar Lab that the team at the University of Luxembourg has, and that's a pretty good test bench, right? Like being able to model. I don't know if iSpace has something similar. I would venture to guess that they do. So lighting, we can deal with that. Obstacle distribution, we can deal with that. Ground interaction is the tricky part to get right. And yeah, I would say that maybe I'm biased because my main research line has been terrain mechanics for a long time, but that's very hard to get really have precise information about. And even when you do, it's hard to model here on Earth because, as I said, highly dependent on temperatures and humidities, and repeatability in terrain is just not good. Yeah, I don't know what else would be interesting to know. I mean, if we look at the skylights, understanding a bit better which ones actually we're going to explore and how entrance look like for those. And I know this is kind of like a broad question, like, okay, sure, fine, just understanding what is it that you're going to explore. But we saw so many different concepts in terms of robotics for exploring different skylights, vertical, descent, some others that may look a little bit more, user-friendly, where you can just probably drive in, having more information and seat information there. But yeah, I kind of, that's probably what I would think of from a robotics standpoint. I'm not a planetary scientist, and probably if you ask a planetary scientist, they will give you a completely different answer.
Thanks a lot.
I don't think we have. other questions. Anyone else has a last minute question? Raise your hand or there you go. There's a hand. Mark has a question.
Hi. I don't know if you see me.
Yes, I do.
Hello, David. Thanks for your presentation. I would like to come back to the question raised by Marcus on the H2O2 monopropellant. 10 years ago, we developed with NAMO and Saab monopropellant rocket engines, and it was very reactive. This was a question raised by Marcus. We tested in a long duration fire, in throttling, in pulsing, and we had like immediate reaction on the engine. So H2O2 might be a quite good solution for the hopper. By the way, Marcus, glad to see you, even if it's through Zoom. I'm glad you say you are working on a monopropellant with H2O2. The second question, it's not a question, it's a comment, is, David, did you ever try to analyze the movie of Apollo 16 when Tom Young was playing with a rover as if he would be driving a F1 car? And you can see how hard it was for him to drive the rover at high speed, not only because of a lack of adherence to the soil, but also because he was bouncing all over the trajectory. And I think by analyzing the movie, you could already try to derive side dynamics of such a rover for the trip perform and the speed it could raise. And I'm convinced there is a lot of information available at NASA or internet on this as a document or even movie. And I think it would be good to better understand the effect of high speed on the moon surface.
Yeah, indeed. Actually, that's what we did 2 years ago. So since we didn't have, so when we started asking ourselves the question of what does it look like, or what happens when we start to move faster on this, on the moon in particular, and low gravity celestial bodies, we didn't have a lot of evidence. And the only evidence, unfortunately, the lunar roving vehicle didn't have any they weren't tracking the performance as much. There were no like load sensors or anything we could actually use. So all we had was, as you said, the movies that were recorded and the post-mission reports. So yeah, I spent a good month just going over all the Apollo post-mission reports and looking at the video, and we extracted some lessons learned. If anyone is interested on those, they're in my PhD thesis, which I'm happy to share. Just drop me an email. And as you said, basically what we can like extract it in terms of lesson learned is like, when you move fast, it becomes bumpy, right? So you need something to mitigate that. And but not only that, so braking distances become a lot longer as well. So they were actually double those that were measured here on Earth. So it takes a lot longer for you to brake, and it's a lot harder for you to steer. So some of the interesting tests that they did during the Apollo missions were the different steering configurations. So they had the traditional like Ackermann steering, just 2 front wheels, but they could also steer the back wheels too. So we took into account a lot of that as well, a lot of side sleep. And of course, during Apollo, most of those problems were solved just by the astronaut getting out of the vehicle and, just holding it and moving it to a different place. That's something we cannot do. So in terms of how we use that information, what we did is something I didn't mention, but not only we look at the aspect of terrain mechanics, we look at the aspect of suspension design. And we come up with something that we called the mechanically hybrid suspension, just because we needed to come up with a name for it. And that's to have, if you have in mind the traditional rocker bogie configuration that most rovers use, just add spring and dampers to that, in an attempt to actually hold those wheels as close to the ground as possible and mitigate all the negative effects of those vibrations and of that bumpiness. So that's a great point, and that's precisely what we did. Yeah.
If I may just raise a short question on this, you didn't look at the type of mechanical hopper, which means if you look at the main difficulties of driving on the soil with all the rocks and the obstacles, there was I think before the Apollo mission went to the moon, many studies performed by NASA on a hopper which would just jump and then coming down slowly on the moon, recover some energy to keep jumping on and on. And the advantage of the system is you can cover a huge area quite quickly with, if you have the right instrument, get a lot of data on the potential resource you could find in the area. And it's nearly purely passive. You just need to sometimes stop on the moon, I don't know the word, we put the spring on the right position to restart it, right, just with a small electrical engine.
Yeah. I mean, I didn't mention this, but the whole idea of the drone actually started with a hopper. We wanted to do a hopper, and the reason why we moved to a drone is because landing on the ground is hard, and when you land on the ground, particularly on these regions that I mentioned, permanently shadowed, you don't really know where you have an idea where you're going to land, but you don't know where your land is actually valuable from a scientific point of view, right? And same for skylights. I mean, I've seen some concepts where you just hop into a skylight, but pretty challenging if you ask me. And then from a point of view of just thermal design, not having to touch the ground makes things a lot easier. So we stayed under sunlight. We just cover a very simple flight path and try to keep it as kind of like the drone design as dumb as possible. Just, keep all the complexity in the vehicle of the rover that goes along with it. It simplified the design quite a lot. And that's why we try to move away from actually having to touch down on the ground. But it all started with that in mind. So, making a hopper that is actually lightweight and smaller than the concept that we've been seeing since Apollo of like reusing landers, right? Or moving big masses from point to point. And I know there are people working on the hoppers. So this was also an attempt to kind of complement what other people are looking at.
Perfect. Thank you very much, David. Sorry, I arrived late at the beginning. I was supposed to do the introduction, but then I will do the closing remarks. So it was really good presentation. The video of the seminar will be available on YouTube, I think within a week. I know some people were curious about the slides. I think you can send an email to David and he will be happy also to share, or you might also even put them on the website. This is up to David, we'll see. And this was indeed the presentation for the Lunar Hub. There are other hubs that will pop up within eSpace soon. So follow also us on our social media, so then you can also learn about the other projects that are taking place at eSpace. And congratulations again, David, for this great presentation today. Thank you.
Thanks a lot.
Goodbye.
Thank you, everyone.